Hello everyone, I'm Eugene from NYCU, the first author of this paper, titled Cross-Resolution Propagation for Foveated Video Super Resolution. Firstly, I want to lay out the motivation for us to carry out this work. It is evident that the consumption and demand of high-resolution content will only get larger over time. However, the delivery of such content has physical limitations such as computational resources, for example real-time rendering, and most importantly, communication bandwidth. It is also evident that another emerging trend is the widespread adoption of augmented devices. Eye trackers are usually found on such devices help in the reduction of rendering high-resolution content. We explore if such eye trackers can be applied to drastically reduce the bandwidth required for video transmission. Next, we would like to describe how we tackle this problem. It is evident that video super resolution shows promising results with many devices adopting this technology. In our work, we adopt basic VSR++ as the base model in our FVSR pipeline, as it is also the state-of-the-art architecture at the time of writing. We push it to perform 8 times VSR as our objective to super resolve pixels that are in the peripheral regions. Since the human eyes are unable to resolve the extra resolution in the peripheral region, or what we call the peripheral vision, we can exploit this property in the design of our FVSR pipeline. Through our approach, we can save up to 13.7 times of the original transmission bandwidth of the 1080p video without compromising its original visual quality. Here we show the architecture of cross-resolution propagation for the task of FVSR. In the top half of the architecture, we have a convolutional VSR pipeline motivated from the design found in basic VSR++, composed of flow warping modules integrated in the feed-forward deformable convolutions. First, pixels of the foveated regions at the origin resolution is encoded and is fed to the entire architecture through a feedback pathway shown in purple. Second, features from the timestep t is propagated to timestep t+1, such that features that correspond to the gaze region can be targeted towards regions of future frames that correspond to the pixel position at the gaze region at the current frame. This ensures that pixels that surround the gaze region in the future frames, which is not in the past foveated region in our work, looks visually pleasing. Here, we show the feature aggregator, which is also a building block of our architecture. It draws aggregate features from different pathways. For example, forward aggregator path features from the feedback pathway, prior frame information from the warp feature pathway, incoming low resolution features from the low resolution pathway. Next, we show the output block. The encoder foveated region features HT is aligned to indexing the position using the gaze coordinate PT of the attached eye tracker. To minimize the computation cost, regional convolution is applied to the concatenated features to generate the forward field features HT. Tilt. Before the generation of the final frame, forward field feature is passed through the feedback pathway to provide context from the foveated region to the feature aggregation blocks to super resolve future frames. Here we show the quantitative and qualitative analysis of our work. So from the quantitative results, we can show that CRFP outperforms the direct adaptation of basic VSR++. On the right, we can see the qualitative analysis of our approach. We can see that the foveated region is well capped at the past foveated regions. Lastly, we would like to show a demo. So the simulation is a CRFP under additive Gaussian noise with different standard deviations, where sigma equals to 10 in this video, and sigma equals to 50 in this video, where the noise is higher in this video. And next, we can see that when sigma equals to 100, the passing motion is well capped as well. So thanks for listening, and here's our tutorial for our work.